Okay, hello everyone. Hello everyone. So this is another video on DFA design. So we have this language here, and we want to design a DFA which accepts it. So the language is on the set of strings 0, 1. So the strings are using this alphabet. And the restriction in the set builder notation is for the number of zeros mod 2 in the string. So in the string to actually be different from the number of ones mod 2 in the string. Okay. So how are we going to design a DFA which accepts strings that are in this language? Like, what's a string that should be in this language? Something like 0, 0, 1, because the number of zeros of W mod 2, well, that's 2 mod 2, which is 0. Then the number of ones in W, number of ones in W mod 2, that's 1 mod 2, which is 1, and so this is clearly different. And so this is in the language, but something like 0, 0, 1, 1 or 1, 0, 1, 0, that's not in the language. Okay. So when it comes to a language like this, it's good to think about it a little bit. And at some point, what you might notice is that there's kind of just like a finite number of cases in terms of N0 mod 2 and 1 mod 2. And there's a finite number of cases where those two modulo operations are different, right? So what do I mean by that? Well, if you have um, N0 mod 2, right? So the number of zeros in the string W mod 2, then this can either be 0 or 1, right? And then similarly for N1 mod 2, then by modulo arithmetic, this can either be 0 or 1. And so really we have four possible kind of combinations, right? We have when n0 mod 2 is 0 and n1 mod 2 is 0, when n0 mod 2 is 1, and when n1 mod 2 is 1. So this is when actually the modulos are equal. And then we have two other cases, so that's like two cases. And then we have two other cases when the modulos are different, right? So that's when n0 mod 2 is 0 and n1 mod 2 is 2. And also when n0 mod 2 is 1 and when n1 mod 2 is 0. Right? So this is when they're different. So we have also two cases. So in total, right, we have sort of four cases to consider. And because our DFA is sort of finite, it's nice that we've isolated four cases because now we can try to see if we can encode each case within a state, right? So the typical trick, one possibility that you can try to do when you're doing DFA design is try to exhaustively um, identify cases, right? If the number of cases is finite, cases is finite, then it's probably a good idea to try to say that uh, for each case, encode it into a state. Okay, so what do I mean by encode? Essentially, in this case, what we kind of want to do is we kind of want to have four states, basically. So we kind of want to have four states. One state where n0 mod 2 is 0 and n0 n1, sorry, n1 mod 2 is 0. Another one, so if I do like the horizontal axis is the change in the number of zeros. So n0 mod 2 is 1, and n1 mod 2 is 0. And then let's do the vertical axis kind of represents the change in number ones. So n0 mod 2, that's going to remain 0, but now n1 mod 2, it's going to be 1. And then same thing, right? So here on the vertical or y-axis, we're not going to change the number of zeros. So this is going to stay n0 mod 2 is 1. But the number of ones, the case is going to flip, right? We're going to have a different case where the number of ones mod 2 is 1, right? And so this kind of encodes the four cases that we kind of care about. Now, I mean, it's great to like label states with names and say like, okay, this state is going to do this. But really the way that you actually implement the logic is by adding in the edges. So the edges, you don't just automatically create a DFA that works by putting the labels. To actually make the logic work, you have to fill in the edges such that they correspond to the logic. So how do we do this? Well, kind of using this logic of like the horizontal axis should be changes in zeros, and the vertical axis should represent changes in ones. So that kind of tells me where the transition should be. So if the horizontal axis represents the changes in zeros, then if I have in this state n0 mod 2 is 0, then to go to n0 mod 2 is 1, I have to see a 0, right? And if I want to flip back from n0 mod 2 is 1 to n0 mod 2 is 0, then I must see another 0. Okay. And then similarly for these other two states across the horizontal axis, right? So the only way that I can switch from n0 mod 2 is 0 to n0 mod 2 is 1, if everything else remains constant, is by having this transition, right? So this is like one of the very simple DFAs that we typically see, right? I mean, one of the simple DFAs that we usually see is something like you transition for zeros and you keep the ones sort of, you transition for the zeros and you keep the ones as self loops. So the ones don't affect the modularity of the number of zeros, but I mean, the numbers of zeros, of course they do, right? And so here you have an even number of zeros. How do you get an odd number of zeros? Well, you see an extra one, right? You go from like 2 to 3 or from 6 to 7, right? And so that's this logic just being implemented here across two pairs of states. And now I'm just going to implement, this kind of logic, the flipping of a switch, the flipping of a bit, which represents the modulo 2 here, but for the sort of vertical axis, right? In that case, for the vertical axis, I need the number of ones to change, right? So if I need the number of ones to change from even to odd, then I ought to see a 1 for that to happen, right? So for instance, if I had up until some point in my string an even number of zeros and an even number of ones, then the way to go to an odd number of ones is if the next symbol I saw was a 1, right? That's how I would get there. So that's what I'm going to do. I'm going to do a 1 here. And then similarly, to go back to an even number of ones, then I need a 1 transition here. And then the logic, the argument is exactly the same for this pair of states. And notice what we've actually done is we have created a DFA in the sense of like determinism, because for each of these states, right, for each of these states, I have two outgoing edges. So for instance, in this one, I have 1 and 0, and I have one outgoing edge for each symbol in my alphabet. In this case, remember, we're assuming the alphabet is 0, 1 here. Okay, so what's missing though now is, I mean, I don't have a start state and I don't have any accept states. So the accept states are maybe a bit easier to justify. The accept states should be the cases for which um, the string satisfies the condition or the property in the language. So remember, that's when the modulos are different. So that's these two cases here. So I'm going to add them as accept states. And I'm not going to add any other accept states because here and here, the modulos are the same. Now, how do you choose the start state? So for choosing the start state, you essentially have to think in which case does the empty string fall, right? So that's kind of an important thing. In which case does the empty string fall, right? Why? Because why do I care about this? Because if my DFA receives the empty string and nothing else, it's just going to stay at the start state, right? So if on my input tape, I just get the empty string and I'm at the start state, then my start state is going to say, okay, I'm just waiting for the first symbol. Remember, the empty string or epsilon doesn't really count for, what doesn't count for a symbol, right? Symbols are either 0, 1 or A or B, right? So it's as if I didn't input anything. I didn't input anything using my keyboard of size 2. So then my sort of machine is still waiting at Q0. So if it's waiting at Q0 and the states kind of represent information, then you kind of want Q0 to represent the information for the empty string. So for the empty string, right, the number of zeros in the empty string is 0 because there are no zeros in the empty string. So 0 modulo 2 is 0, and there are no ones in the empty string, right? So I have 0 ones in the empty string, so modulo 2, that's also 0. So what that tells me is that the empty string um, uh, is in the case, the empty string is in the case where the number of zeros and the number of ones, mod 2, are both equal to 0. And so that's this case here, which is why I'm going to put a start state here, right? And then the kind of logic works out. Because for instance, if I have the string something like 0, 1, 0, 0, 1, then let's see what happens. So I start at my start state here. And so far I've not seen any zeros or any ones. So it makes sense that I'm in N0 mod 2 is 0 and N1 mod 2 is 0. Then I see my first string, I see the 0, I see my first symbol, sorry, is 0. And so I go to this state. So now my mod 2 for 0 is 1, but I still haven't seen any ones, so then it's 0. Then I see this 1, so I go down here. Then I see this 0, so I go back here. I see another 0, I go back here. And I see a 1, so I go back here. And so I end up in N0 mod 2 is 1 and N1 mod 2 is 0, which is correct, right? Because I have 3 zeros. So 3 mod 2 is 1, and I have 2 1s, so 2 mod 2 is 0. And so I end up in the correct state that's sort of representing the correct information. And, you know, the modulos are different, right? So that's why so then it's correct that this is an accept state. Okay, and so this is how you would design the DFA for this language, showing as a result that this language is regular.